bar magnet as an equivalent solenoid. We know when current passes through a solenoid, we know what is a solenoid? It is an insulated coil of many turns. Insulated coil of many turns in the form of a cylinder. When current passes through the solenoid, it is producing magnetic field, and the magnetic field produced by a solenoid is almost similar to magnetic field produced by a bar magnet that we have seen in the last chapter. Here, in this chapter, we are going to prove the magnetic field intensity produced by the solenoid on an axial point is equal to the magnetic field intensity produced by a bar magnet. Consider a solenoid of length 2L. It is shown in the figure there. So radius is A. It is shown here. Carrying a current I. I current is flowing through it. Consider a point P at a distance r from the center of the solenoid. Let small n be the number of turns per unit length. Our aim is to find out magnetic field intensity at a point P distant r from the center of the solenoid. Just imagine solenoid is placed at the origin and the center O it is marked there. Total length is 2L, therefore half length towards the left of the origin and half length towards the right of the origin. In order to find out magnetic field intensity at a point P, just imagine solenoid can be divided into small strips of thickness dx as shown in the figure. This blue strip of thickness dx as shown in the figure. Consider a small strip of solenoid of thickness dx at a distance x from the center. We studied in the last section the magnetic field intensity produced by a small strip of coil at a point P at an axial point. B is equal to mu0 Ni a squared divided by 2 into a squared plus x squared whole to the power of 3 by 2. This already we derived. Where x is the distance from the strip to the point P, A is the radius of the coil. Here in this case, in this strip, number of turns will be, we know, small n into dx, that is the total number of turns. I is the current flowing through it. Substituting that one, magnetic field intensity at a point P, due to that small strip of coil carrying current, dB is equal to mu0 Ni dx a square divided by 2 into r minus x whole square plus a square whole to the power of 3 by 2. We know r minus x. It is the distance from small strip to the point P. The total magnetic field is obtained by summing over the magnetic field due to all elements from x is equal to minus L to x is equal to plus L. Therefore, total magnetic field intensity B is equal to mu0 Ni a square divided by 2 integral minus L to plus L dx by r minus x whole square plus s square whole to the power of 3 by 2. Considering far axial field of the solenoid, the distance from the solenoid to the point P are very large compared to the radius A, and similarly R is very large compared to the length of the solenoid. We can neglect the radius term and we can neglect x also in that above equation. Since if L is very small compared to R, we can neglect x in that equation. Therefore, we will get the equation r minus L whole square plus a square whole to the power of 3 by 2 can be approximately written as r cube. Therefore, B is equal to mu0 Ni a square by 2r cube integral minus L to plus L dx. Integral dx is equal to, we know, length of the solenoid only 2L. Substituting there, B is equal to mu 0 Ni A square 2L by 2 R cube. We know N into 2L. That is the total number of turns, capital N. Pi A square. A square is there. We have to multiply by pi. Therefore, we have to in a denominator also we have to multiply by pi. Pi A square is equal to capital A. And we know magnetic moment M is equal to Nia. Substitute for capital N there. And instead of pi A square you write A there, and in denominator you write multiply by pi. Finally, we will get B is equal to mu 0 by 4 pi 2m by r cube. This is the magnetic field intensity on the axial position of a solenoid if the solenoid is very small and size of the solenoid is very small. In the case of a bar magnet also, the magnetic field intensity on the axial position will be mu 0 by 4 pi 2m by r cube.